In this work, we are looking at the process of electronic energy transfer. Specifically, we are comparing the electronic couplings derived from molecular quantum electrodynamics and Förster theory that serve to regulate this process. Molecular quantum electrodynamics is a theory that treats both matter and light on equal quantum mechanical footings. Within this context, QED has provided a platform with which to describe electronic energy transfer through a unified theory which links regimes of EET that were once thought to be distinct mechanisms, that is, near-zone, non-radiative energy transfer, and far-zone, radiative energy transfer. The electromagnetic coupling tensor describes the spatial dependence of the coupling that mediates EET. Highlighted are three distance dependencies. This is the near-zone contribution, which dominates when the donor-acceptor separation distance r is much less than the reduced wavelength of the mediating photon. And here we have the far-zone term. Within this theory, we see a contribution from this intermediate zone term, which plays an important role when r is approximately equal to the reduced wavelength. These are the orientation factors that define the directionality of coupling. To undertake this investigation, we carried out quantum dynamic simulations of exciton migration. The simulations are performed in the site basis, and off-diagonal elements of the Hamiltonian correspond to electronic couplings between molecules. The study focuses on comparing QED-derived couplings with the classical Förster couplings. In this set of simulations, we employ a 2D Brickstone lattice of transition dipole moments which are represented by arrows. The parameters of the lattice are Rx and Ry. To investigate when the intermediate and far zone terms play an important role in EET, we consider three different lattice parameters, namely 2, 5 and 10 nanometers. Here we have the coupling landscapes of the individual contributions to the tensor for the lattice parameters of 2 nanometers. Far zones on the left, intermediate zone in the centre, and the near zone on the right. These landscapes can be understood by considering the nature of the mediating photon. Using the Helmholtz theorem, any vector field can be separated into irrotational and solenoidal components. For this work, the Coulomb gauge is employed when describing electromagnetic fields, and hence the irrotational component disappears. The result of the transversality associated with the equation in the box is that the electric and magnetic field vectors are orthogonal to k, the propagation vector. However, when the emitted photon is still close to the donor, its short path means it is strongly subject to quantum uncertainty in vector momentum, including direction, and hence transverse and longitudinal components contribute to the EET process. However, in the far zone, behavior is consistent with a fully transverse field. Due to the contributions of photon fields with longitudinal character in the near zone, coupling of type A can occur. In the far zone, the exclusively transverse electric fields only couple transition dipole moments whose orientation is shown in B. This explains the different coupling landscapes as described in the previous slide. We now show a movie of the 100 femtosecond trajectory based on the QED-derived coupling and lattice parameters of 2 nanometers. The exciton moves symmetrically away from the central molecule in a wave-like motion with the favoured directions of energy transfer consistent with the coupling landscapes. It is more informative to look at plots of the differences in the dynamics for the two coupling mechanisms. It is quite apparent that the population change that occurs in the central region of the lattice is the same for the two ET coupling models under investigation. Small differences in the spatial dependency of the energy transfer can be seen in some regions, particularly early times in the dynamics. This difference is effectively washed out as time goes on. Now we look at the differences that occur when the lattice parameters are increased to 5 nanometers. Here we can see the difference in the spatio-temporal dynamics for QED and Förster-derived couplings are more pronounced and long-lived. These differences are now even more evident in the case where the lattice parameters are increased to 10 nanometers. Our results show that as the lattice size is increased by means of changing the distances between the molecules that comprise the lattice, the intermediate and far zone contributions to the coupling start to play important roles in the spatial and temporal exciton dynamics. Inclusion of these terms may then become important in accurately describing exciton dynamics in mesoscopic structures such as quantum dot arrays.